Good morning, everyone. Welcome to session 30 on CO2 emissions reduction, hydrocarbons, E&P in operations. Decarbonization as a topic has taken center stage over the last couple of years, and where better to start than to start from the source, which is at the source of extraction and production of crude and gas. In that context, the role that E&P industry will play in decarbonizing their operations is going to be very critical. We've all heard about CCUS as the key lever for driving this decarbonization, but there are more decarbonization levers that will also be required, not just from the perspective of decarbonizing their internal operations, but for the fact that India's journey and India's pathway to net zero will have a meaningful role wherein CCUS will have a big chunk to play. So with that context, today, my name is Manan Shah. I am a co-chair for this session along with Manish. And what we want to do is we have an interesting panel of esteemed speakers who will talk about some interesting ideas of how E&P companies can drive decarbonization. Manish, do you want to add to this?
Good morning. Welcome everybody. My name is Manish Shandilya. I am a co-chair along with Manan. Manan has given a very interesting beginning. We have an eclectic mix of people having experience in various areas. As rightly pointed out, low carbon strategy is needed for a sustainable future. And welcome everybody, and without much ado, Mr. Santhosh, kindly. Mr. Santhosh Kotni is a manager from Hindustan Petroleum Corporation Limited, and he'll be sharing his presentation on CO2 emissions to methanol, insights into catalyst and operating parameters.
Good morning, everyone. Thank you, IEW, for this opportunity to present our work. Actually, I come from Hindustan Petroleum R&D Centre, which is located in the South India. Today, I'll be touch upon the catalysis part of CO2 conversion, basically the CO2 to methanol. So when it comes to measure global sources of CO2 emissions, we have different contributions from different sectors. Where industry contributes around 19%. I come from an industry where you have thermal power plants, steel plants, cement industries, fertilizer plants. You can consider as an industry contributors, and petroleum refineries, where I come from, contribute around 4 to 5% of CO2 emissions. Since I belong to refinery, this number is very significant or important to us. So in the refinery itself, when you look at the CO2 emissions, we have major source of CO2 emissions from hydrogen generation, around 5 to 20%, and FCC, which contributes around 20 to 35%, and the furnaces and utilities together will contribute majorly 70 to 80%. So since we have a major sources of CO2 emission, we also should have a strategies or supported by the technologies for the reducing the CO2 emissions. So when I say strategy, it can be reduction. It means that it should be supported by clean technologies where efficiency should be better, and CO2 overall CO2 emissions should be less. Or it can be replaced. You cannot replace completely, but suppose hydrogen generation unit, if you consider, you can think of contributing it from water electrolysis. So it can be a greener alternative. Otherwise, reuse, because since you cannot replace everything or you cannot avoid CO2 emissions, so other ways that you have to convert whatever you are emitting. So we call it CO2 utilization. So when it comes to CO2 utilization, why CO2 is so big, the kind of a discussion, because people consider CO2 as a tough molecule. Tough, nothing but because when you look at Lewis dot structure, basically octet is achieved, means oxygen and carbon are having 8 electrons each. They are basically neither hungry for electrons nor overloaded, and that's why it is considered highly inactive, inert molecule, because if you look at it's thermodynamically stable. It has very high low delta G of minus 394. But is it really that tough? So if you look at the nature has shown us the way. Basically, plants are converting this CO2 to carbohydrates through catalysis route. So even if you look at the industrial CO2 utilization, you have urea synthesis, salicylic acid, which is a pharma ingredient, And also you can use CO2 for the polycarbonates, which is for a plastic. So, but they all contribute only 4% of total CO2 emissions which are coming out. So there is a huge space, to develop a technology for further conversion of CO2. So this picture looks complicated, but to simplify it, if you look at the right side, extreme right, basically the CO2 molecule, we know it's a linear in nature, which is bond angle is 180. To activate that, the simple thing is that you have to change its bond angle. Basically, this picture shows that when it goes from 180 to 90 degrees, basically you can activate or make the molecule reactive. So how to change the bond angle? You need a surface where the catalyst comes into the picture. So you bring that CO2 molecule close to the catalyst surface. So it should not be too strong. It means that it should not be too strong adsorption. Basically, it will stay only on the catalyst surface, or it should not be too low interaction because it will not even talk to the catalyst surface. There should be an optimal energy that you have to design for your catalyst surface. So where basically it interacts nicely, and you can actually do some kind of electron transfer, and you can change the bond angle. So that's where the catalyst plays a role. And when you have the catalyst, so CO2 can be converted into different products because you're trying to activate the CO2 to different products. So it can be carbon monoxide or olefins or alcohols or alkanes or hydrocarbons. But when you look at this, the 4 parameters of rate of formation, selectivity, energy efficiency of the final product, or the TRL levels. So you have a carbon monoxide or the methanol which can be targeted. So even also methanol comes into the hydrocarbon pool. It has good, the octane number. So considering that, the methanol can be a good choice from the CO2. And when you select the product and when you are activating the CO2, so based on the product, you also have to choose the pathway. So there are different ways you can activate the CO2 molecule or catalyze the CO2 molecule. One is electrochemical. Suppose if you are looking for the carboxylic acids or CO kind of thing. Since we are looking for the methanol, so we can select the thermochemical route, so where actually methanol can be selectively produced. When I say catalytic route, again the catalyst plays an important role. As I mentioned previously, so the activation comes from the changing its the structure. So the bottom side of the picture, when you look at the CO2 comes and adsorbs on the the catalyst surface, which is very linear. And during the interaction, there will be a change in the bond angle, and subsequently there will be hydrogenation of the molecule takes place, and finally you get methanol. So these are the 4 important steps. First, you have to bring the molecule close to the surface. Then you have to change its orientation, then hydrogenation, and get the product desorption. So since I'm talking about the catalyst part, so basically our intention is to showcase, in R&D, whatever our capabilities in designing a catalyst for any given kind of a process. So basically we try to understand the mechanism. Here, as I mentioned, the adsorption is one of the important parameters. When the CO2 comes close to the catalyst surface, if you look at alumina or kind of a silica, which is kind of a supports, the numbers are very high, 700, 600, something like that. It means that it doesn't have a good communication with the catalyst support. But the right side, when you keep improving, incorporating kind of a metals like copper or zinc, which are well known in the system, you can bring down the adsorption energies. It means that you can keep activating the CO2. But what we did is that before we do the experiments, we have carried out a simulation studies by incorporating several promoters, and we try to identify the possible promoter. If you see the right side highlighted column, so where we brought down the adsorption energy from around 700 to 36. It means that we are trying to tune the adsorption of the CO2 with the catalyst surface. The optimal adsorption energy gives you basically the nice interaction between your CO2 and the catalyst surface for the better activation. So it's not so. Once we know what kind of the supports or promoters are helpful, we can actually do the experimental validation. So I'm unable to give the values, but the idea here is to say that out of 5 catalysts, the top one is very strong adsorption, the bottom one is very weak. So optimal one is the third one. So the same thing you can validate them through experiments. Like on the left side graph shows that you can measure how much CO2 is getting adsorbed onto your catalyst surface. So the ideal one we have taken, and we have started basically evaluating the catalyst. So once the catalyst is designed, the next step is basically you have to test the catalyst. So because there should be a benchmark, like how much conversion you can achieve. So that is very important, or how much selectivity you can target. So these two parameters are very important when you're talking about the CO2 conversions. So when you look at this methanol formation reactions from the CO2, it's a highly exothermic. So being exothermic, it favors at low temperature. The right side graph basically talks about the theoretical kind of a scenario. Ideally, if you have 100 degrees centigrade, you can achieve 100% of CO2, but provided high pressure, like 300 bar. But this is a thermodynamic point of view, but kinetically also we should look at, because CO2 is being inert, you have to have a high temperature basically to activate the molecule further. So that is why whatever the low temperature will not work, you have to go to higher temperature. Little bit generally works at 200 to 250. So the moment when you go for high temperature, the reverse water gas shift reaction CO formation takes place. So ideally you can say that the highlighted round circle, basically you can target around 20 to 30% of CO2 thermodynamically and kinetically. So and we have developed our own catalyst based on whatever the inputs have discussed, and we actually the HP Cat3 gives the CO2 conversion close to the thermodynamic limit around 25%, and good selectivity for the methanol and good space time yields. So we are actually now developing because after developing the catalyst, now we are in the process of developing the process. Now we are setting up a plant for size of 10 KTPA, where we source our CO2 from our refinery exhaust gases, and then we have a green hydrogen. Together it will go for a fixed bed reactor, and then we convert the CO2. Purpose 19%, but we are targeting greater than 90% with recycling. And we, in the further, we are actually targeting around 30% of reduction in our CO2 in our refineries. So finally, I'll conclude my presentation with this slide on a thought on CO2 to methanol and economic outlook. Because many questions are raised when you convert CO2 to methanol, what is the economic viability? There are three scenarios you can consider. The top, basically, a table shows, basically the technological viewpoint. At the bottom, this is from the feed side. Like, you have feed prices like a CO2 price, electricity price, hydrogen price. In the current scenario, if you look at the technology, the conversion should be ideally 27%. That is max you can achieve. So, and you can target around 70% of selectivity that everybody is reporting. But a future scenario, you can slightly improve in the technological front from 68 to 90%. That is the last one is the theoretical. So where you can achieve selectivity around 100%. But if you look at these numbers and technological or conversion point of view, you don't have much to do. But in terms of the feed prices, that actually majorly contribute to your overall methanol price. If you look at the current price of the CO2 and electricity price and hydrogen particularly, which is around $4 if you are considering from hydrogen water electrolysis. The bottom deviation from market price, if you look at, so basically zero is the one, is the benchmark if you are considering the price of conventional methanol. And if you are producing methanol with the current scenario, it will be $1.5 higher than the benchmark or the conventional price. If you go for the future scenario where slightly you reduce CO2 price from 40 to 20 and hydrogen you get slightly cheaper, then still you can make the methanol, but slightly with a higher price of $0.5. In the theoretical scenario, where you have 100% selectivity, but there is no CO2 price, still you will have the positive price. It means that still the methanol will be expensive, slightly higher than the benchmark. Only it will be possible, like from the studies, what we understand is that so methanol price should be negative. I mean, like you should get a credit for the CO2. So if you are getting around minus $35, that is what actually US federal government does. Basically, when they give around 45Q program. So in that case, you can bring down the cost of methanol negative or cheaper than the conventional the methanol route. So finally, I want to summarize. So CO2 is a tough molecule, but we can activate that with the right catalyst. So we have developed the catalyst based on several studies, simulations followed by the experimental validation further. And actually the catalyst which we have designed, gives the yields and the selectivities close to the thermodynamic limit, and we are going to set up the plant soon. So this catalyst is already patented. Thank you so much.
Thank you, Mr. Santhosh, for walking us through CO2 to methanol. Looks a very interesting and unique opportunity for decarbonization. Next, can I call? We have Mr. Ritesh. Mr. Ritesh is an assistant general manager with EIL, and he's going to talk about novel catalysis for CCU in futuristic green refineries.
Good afternoon, everybody. So, I'll be touching upon the catalysis for CCU. CCUS is a complete term, it's carbon capture, utilization, and storage. But I feel storage is not a very viable option. So, the good part is that once you capture the CO2, you convert it into some value-added products. So, that is a very viable option. Like my previous speaker told, that you can convert it to methanol. And as it is said that CO2 is a very tough molecule, the question is not whether CO2 is a tough molecule or not. The question is what catalyst you are preparing, heterogeneous catalyst generally. And that particular catalyst should have viability, economic viability. So basically the complete LCA process and the catalyst is the key recipe of the catalyst is important when you are talking about converting CO2 to value-added chemicals. So I am from EIL, just to tell you that EIL is an engineering consultancy company, and we are having our own R&D center. And we are aggressively working on biofuels now. We are working on 2G ethanol plants. We have prepared DFR for IOCL, BPCL, HPCL, all the OMCs for setting up the 2G ethanol plants. We are putting up sustainable aviation fuel bio-ATF plant at MRPL. We are already implementing Numaligarh refinery 2G ethanol. And we are also expanding our portfolio in nanocellulose and CCUS catalysis, heterogeneous catalysis per se. So just to tell you that biofuels is future, and this everybody knows. We have limited crude reserves. We need diversifications. And generally, just I'll let you know that when we are talking about catalysis for CCU, we should not ignore the biomass. There are different routes of biomasses, and CO2 is generated. So basically, this CO2, when we are talking about biomass per se, then the biomass is something which we say when we talk about crude or we talk about coal, natural gas, or whatever it is. It has been buried under the earth some 5,000 years back, and it gets converted to crude. And biomass is something which is on a shorter geographical scale. So it captures CO2, we harness the biomass, and we again convert it into the CO2 to the atmosphere or VACs. So there's nothing called carbon neutrality. When we talk about carbon positive, carbon neutrality, or we talk about carbon footprint, it is basically in terms of the geographical scale which we are talking about. So biomass is something which reduces the timeline. So this in essence is called as carbon neutrality. Otherwise, nature has already been very good to Earth, Mother Earth. 5,000 years back, whatever carbon dioxide was buried in terms of cellulose inside the trees, which was buried inside the earth, that is now coming out in the industrial evolution. So just about first, second, and third generation of biofuels, algae is considered a very viable option of removing CO2 in a natural way, because it captures, it harnesses carbon dioxide at a very faster rate. And now we are talking about modified fuels also. The basic concept is when we are talking about CO2, the best part is now people are talking about e-fuels, which we call as electronic fuels to be precise. And there what happens is that you have CO2, and we have National Green Hydrogen Mission 2023. It was unveiled last year by the cabinet. And it is somewhere around 19,000 crore project with an outlay of 400 CR, particularly to the R&D. So you cannot have these two in a simple different compartments. You produce CO2, you capture CO2, not produce it. And then that CO2 can be combined with the hydrogen, green hydrogen basically, and you form e-fuels. So whenever you are combining these two with a proper recipe of the catalyst, that makes a complete sense. And people do debate that, we are still struggling for green hydrogen, we are still struggling to capture CO2, then why we are talking about e-fuels. But the point is, this probably in 1940s, somebody must be talking about crude in the same way. When there was no isomerization, there was no value addition to the refinery. Now the refinery is incomplete. So one day somebody has to think about biorefineries. So when we talk about 2G ethanol plants, we generally say that it's a biorefinery, but it's not a biorefinery. It is simply a 2G ethanol plant. Biorefinery means like in a normal refinery, we have so many units. So you need to completely supplement all these technologies together. And let me tell you, if any oil and gas R&D is working, they are neglecting on catalysis part. So catalysis should be the core recipe, because until unless you have a suitable catalyst, how can you work upon it? And we generally talk about a single catalyst. We talk about the reactions. It is not, we are not chemists. We are basically process engineers. So we need to convert from the chemistry to the normal biorefinery. So just talking about catalysis without talking about LCA is also an absurd idea. We always should talk about the LCA part in supplementing the basic catalyst part. So just to tell you that, in 1992 in the Rio Conference Earth Summit, we started up with, that was the first Earth Conference. Then we talked about Kyoto Protocol. Then we have Conference of Parties COP. And just to let you know that we generally say that a refinery has 4 to 5% of CO2 emission. But again, the refinery is a consumer of, it's again the gate to, well to the gate. So we cannot just say how much CO2 is produced in the refinery. So the TPS, the thermal power plants are producing CO2. We need to take into account that CO2 also. So then we can only say that particular fuel is carbon neutral or something. Like for green hydrogen, we generally say it is considered as green hydrogen only when the definition given by MNRE is 2 kg of CO2 per kg of hydrogen, and that too from field to gate. So that's a very stringent definition. You, just harvesting the biomass, then transporting it into refinery, then converting that in particular process, and finally delivering it to the customer till the refinery gate, biorefinery gate. So the complete process should have 2 kg of carbon dioxide emission. So when we are talking about biofuels, generally in green hydrogen also we talks about electrolysis. People in India are very hungry about electrolysis. Everybody is talking about electrolysis. But MNRE in its National Green Hydrogen Mission Policy had clearly stated that biomass is also a very viable option. So there are two routes now, biomass and the most neglected part, and the electrolysis, which everybody is talking about, that we should reduce the cost of electrolysis and everything. But when we are talking about biomass with an agrarian country like India, it can be very beneficial. So that's only the point to ponder about, because biomass has an aggregation, collection problem. So once that problem is addressed, then I don't think e-fuels is a very, it will be a reality soon. India do have its biomass, but the only problem is its segregation. So if we have a segregators also in place in the policies, then definitely e-fuels can be a reality tomorrow. So this is just simply that nature also, there is a biological way, algal roots, industrial use. Then we have direct air capture. I'll tell you in detail about that in the future slides. So just about that, there are different viable options for capturing in refinery: amine-based capture and absorption. Then we have organocatalysts for absorption of CO2 from the flue gases. We have direct air capture. So once we have captured the CO2, better to convert it into VSEs using a suitable catalyst. Now, when we're talking about this advanced heterogeneous catalysis, there are different pathways: aqueous and non-aqueous electrochemical. This is just to make you familiar of what different pathways we can encounter. We can have homogeneous catalyst, we can have heterogeneous catalyst with metal organic frameworks, photocatalyst. One of my speaker will speak about biocatalyst, which we call enzymes basically. What enzyme do? They lowers the activation, and catalyst reduces the activation energy. So the similar process is happening in our body as well as in the nature through enzymes. So we are basically replicating, and as we all know that we can do a heart transplant, but we cannot make a real pump which is as good as our own heart. So we cannot compete with enzymes because they work in the nature, but definitely catalysis as a per se field has developed to a very large extent. So my suggestion is that every oil and gas industry in India should have a dedicated R&D for heterogeneous catalyst development, or you can say for homogeneous. Then we have photocatalysts like titanium oxide in semiconductors. And definitely, I'm talking about the biological part in the last strain-specific algae, cyanobacteria, enzymatic biological catalyst, like carbonic anhydrase. My next speaker will definitely shed some light on that. Then this is just to let you know, this is at a very molecular level, that you talk about picometer, nanometer, and in terms of the time scale, how the catalyst will interact with the molecule. Because we being chemical engineers, we already talk about the mass transfer which occurs, which is the rate determining step. So whenever we are talking about rate determining step, that plays a particular and a pivotal role whenever we are talking about a catalyst. Then, we can convert CO2 to e-fuels, or we can convert it into value-added chemicals. Now the question is, what value-added chemical? We can go for, carbon dioxide methanation. We can make methane. We can use FT process. FT is a very, for diesel range compound, FT is a very, for even if we go for gasification, then FT is definitely, a viable option. Then the point is that we can have fixed bed or fluidized bed. One more point I want to let you know, that whenever we are talking about catalysis for fluidized bed, generally the catalyst remains the same. The basic thing is the mechanical strength of the catalyst. Because whenever we are talking about fluidized bed, the attrition comes into play. Because if you are having a higher attrition and the economic losses, whenever you have fine losses of the catalyst, that reduces the economic viability of your fluidized bed. So whenever we are talking about fluidized bed, then the mechanical strength, when we talk, I'll just let you know in the next slide, that is basically the metal-metal interaction of the catalyst with the, that support. That should be very, very strong, because otherwise you will have losses in the cyclones over the bed of fluidized bed, and that will really reduce, because catalysts are, exotic things, they're costly. So you cannot afford to lose them in a fluidized bed reactor. So just to tell you that the parameters which are very important, definitely catalyst efficiency and scalability is there. Scalability in catalyst is not that important, but the important thing is you should have proper active site regenerability. It's stability. Stability is important for fixed bed also, but when we are talking about fluidized bed, it gains more importance. Then we have absorption strength, surface to volume ratio, metal-metal and metal support interaction. But now the catalysis field has grown to such a, a basic framework is now, nobody talks about nickel alumina catalyst now. It is very cheap. It is, cleavage of carbon is very good with nickel. But whenever we are talking about catalysis now, enhancers, supporters, all these things have come into play. So we have to particularly play with these process parameters. And it's just to let you know that it is okay. Just I'll let you know in the next slide, I suppose. Yeah. So I've just let you know about some of the modifiers like magnesium, lanthanum, cobalt, or chromium. So enhancers, supporters, your inhibitors, which can inhibit your coke gasification coking reactions, and which can favor coke gasification reaction. First is that the catalyst should stop the coke to settle on the active sites. And the second is, if the coke has been sitting over your active sites of the catalyst, then the coke gasification should occur. So it is, we can call it in situ, like in FCC we have a regenerator. You don't need a regenerator if you have a very, robust catalyst. You should have in situ generation of carbon, that we call it coke gasification reactions. Because whenever you're dealing with, bio oil or anything, definitely they're very coke forming. Whenever you're talking about carbon field, it's free of sulfur, but it's very, very coke forming. So you need to have some enhancers and the additives which can gasify your coke. So this is very important factor when you're talking about catalysts. I'm running little short of time. If somebody has questions, they can definitely ask me after this presentation. I'll be happy to answer their questions related to basic aspect of the catalysis which they use. And the basic thing I want to tell you is that among the VACs, there are many VACs which can be formed out of CO2. But we need to limit to those VACs which are having economic viability from LCA. So we have done LCA analysis for different VACs and zeroed down on some of the VACs. And whenever you're talking about catalyst, we cannot jump on the conclusion to develop the catalyst. First, filter it out that what are the economic viability, then you jump on developing the catalyst. Because anyway, you can use exotic materials, platinum or noble metals, and develop the catalyst. But finally, it boils down to whether the refiners will be able to put it or not. So in nutshell, I've tried to comprehend so many things. And thank you so much.
Thank you, Ritesh, for elaborately taking us through the catalytic CCU technologies and conversion to VSC towards a holistic net zero goal. Emphasis was given on catalyst type and design for conversion to VSC, and users were advised to keep economic viability in mind while specifying and selecting such catalyst. This, I would like to invite the next presenter, Mr. Premkumar Sivakumar from ExxonMobil Services and Technology Private Limited. He is a well engineer, and he would be sharing his thoughts and presentation on technical risks and opportunities related to well in carbon capture and storage projects.
Respected session chairs, my fellow speakers, ladies and gentlemen, a very good morning. This is Prem Kumar, a wells engineer from ExxonMobil, here in front of you today to present on the technical risks and opportunities related to wells in carbon capture and storage projects. For many CCS projects around the globe, the legacy wells are the biggest project limiters. While on the other hand, for some CCS projects, legacy wells have proved to be very useful in terms of monitoring the CO2 plume. So, how exactly can we leverage these existing legacy wells in an area to its fullest for the CCS purposes, while also minimizing the risk of CO2 leakage is what exactly I'm going to talk about today. I'll start by introducing you all to the opportunities and challenges associated with CCS projects with respect to wells. I will then explain the legacy wells integrity assessment that we have come up with, supported by a case study, and I will finally close out with the scope of legacy wells post this integrity assessment. So, what exactly is carbon capture and storage, first of all? Many industries have their own decarbonization and low carbon solutions. But as you all know, the oil and gas industry has the great technology of carbon capture and storage, using which we can inject anthropogenic or natural CO2 into a suitable subsurface formation and contain it there, as shown in the picture here. Now, for this purpose, saline aquifers and depleted hydrocarbon reservoirs are being considered as potential CO2 storage opportunities. These sites could be very close to the capture facility or far away, in which case the captured CO2 is transported via pipelines or via ships in case of offshore scenarios. Now, many companies, including ExxonMobil, are scouting for saline aquifer opportunities worldwide. So the main advantage of injecting or storing in saline aquifers is that they offer huge volumes for CO2 storage. But the challenge with saline aquifer is that they are very poorly characterized, meaning we do not know much about the seal or about the aquifer itself. So we would need additional data to prove the integrity of the seal and that we can contain the CO2 that we are injecting there. On the other hand, hydrocarbon reservoirs have a number of wells penetrating them. So the depleted hydrocarbon reservoirs offer us an opportunity for us to repurpose these existing legacy wells either for injection or for monitoring. But the challenge with that is that the legacy wells, just like the faults penetrating the hydrocarbon reservoirs, could act as potential CO2 leakage pathways. Now, as you can see, I'm highlighting the opportunities with both the saline aquifers and hydrocarbon reservoirs, while also talking about the associated challenges. The challenges to any CCS project will relate to three domains. First is the challenges with respect to CO2 capture, then challenges with respect to CO2 injection, and lastly, the challenges with respect to containment of CO2. Our work here specifically focuses on the containment challenges of CO2 in the injected zone. Now, the natural seal and the integrity of the legacy wells is very important to ensure that we contain the injected CO2 in the injected zone. That said, to assess the current integrity of legacy wells, we have come up with a unique workflow in ExxonMobil, the legacy wells integrity assessment, to assess the potential storage sites. Now, the objective of the assessment is not just to understand the legacy wells conditions, but also to characterize them into different groups based on remediation complexity. So this assessment includes three stages. Stage 1, Once the area of interest is defined, we filter out the legacy wells existing within that area. Once we filter out the legacy wells, we extract the well attributes for these filtered out wells from different sources. These sources include a number of third-party databases and regulatory sites. Now, using these well attributes, we perform a preliminary screening, which gives us an executive summary. So this executive summary is nothing but an overview to the area of interest in terms of how many legacy wells exist within that area of interest, what is their type, what is their status, what is their total depth, spud date, and surface location. Stage 2. Once we get the overview of the area of interest, we then pull the well reports from the corresponding regulatory sites. From the well reports, we extract the well construction details as shown in the well schematic in the middle. Stage 3. Once we get the well construction details, we characterize the wells based on the basis of if there are enough verified barriers across the injection zone of interest. We just want to make sure if the injected CO2 can be isolated there or not. Now, this characterization is purely based on the remediation complexity, meaning how difficult it is going to be for us to re-enter and remediate the wells, and it is definitely not based on the CO2 leakage risk. In other words, I could say that this assessment will let us note the project risk of injecting CO2 and not the CO2 leakage risk. That would be a separate study in itself, and that is presently undergoing in ExxonMobil. So for instance, if a well's total depth is falling shallower than the injection zone of interest, meaning it is not going to intercept the CO2 plume at all. So in that case, we would characterize the well as group 1, which we may not remediate. Now, if a well is active or inactive, meaning the wellhead is still in place, it means we still have access to the wellbore, meaning any remediation is still possible. So in such a case, we characterize the well as group 2A or group 2B. It would be a group 2A well if the abandonment is going to be straightforward, or it would be a group 2B well if it's going to need a complicated or a slightly complex abandonment. For example, a well with dual strings, or a highly deviated well, or a well with a fish in it. Now, if the well is already abandoned, we would characterize the well as group 3A if it has enough verified barriers in place across the zone of injection. Or it would be group 3B if it does not have enough or sufficient barriers across the zone of injection. Now, if the well has insufficient information for us to characterize into any of the above groups, we then characterize the well as group 4, which lets us know that the well has high uncertainty. Now, this tool helps us assess a lot of potential areas of interest for CO2 storage. So this tool is developed by the Bangalore team of ExxonMobil, and it is being leveraged by the global CCS teams worldwide. We also make sure to change the basis of characterization as per each country's local regulations. Now, here is a case study that shows what we do. It essentially shows what I just explained. So the map to the top left corner shows the area of interest, for instance. So the area of interest is basically defined either based on the land lease acquired, or the offshore blocks or bits won, or sometimes maybe based on the underlying subsurface structure or the migrating CO2 plume, or even based on some surface infrastructure. Now, once the area of interest is defined, we filter out the wells. So the light blue dots that you see inside the polygon are the legacy wells that we have filtered out within the area of interest. Now, once we acquire all the well attributes from a number of third-party databases and regulatory sites to do due diligence, we will be able to do the preliminary screening and come up with an overview for the given area of interest. So by that I mean, we'll be able to tell the distribution of wells against the well type and well status as shown in the chart to the top right. Additionally, we'll also be able to give a temporal distribution of the wells as shown in the bottom right. So this is to know which wells are old, which wells are fairly new, which will also determine the complexity of remediation and hence the project risk. Finally, once we collect all the well construction details for a high-graded set of wells from this list, we then characterize them based on the well integrity. So this well integrity basis will be based on the local the regulations of each country that we are looking into. So we will end up getting the table that you see to the bottom left, which summarizes how many wells fall into each group based on the available barriers in the well. Now, post the characterization based on remediation complexity, what is the scope of legacy wells? What all can we do with the legacy wells? So after remediation complexity, we can do a further risk assessment for critical wells for CO2 leakage. This risk assessment is essential because when I said characterization, that was purely based on remediation complexity, and it is not directly related to CO2 leakage risk. Meaning, when I say a well is easier to be remediated, it does not mean it is less risky for CO2 leakage, and vice versa. So if I say it's going to be complicated for a well to be remediated or expensive for a well to be remediated, it does not mean the well is more risky. It could just be the case that it is less risky in terms of CO2 leakage, but I'm still going to spend more money on re-entering and remediate it. So a formal risk assessment, which is independent of the remediation-based characterization, is also crucial. Further, we can do a deeper dive analysis and collect additional data for any further technical analysis or risk mitigation needed. And the legacy wells could be repurposed for injection or monitoring and or be remediated based on the outcomes of the risk assessment. And consideration of legacy wells is very important for the development of measurement, monitoring, and verification plans. So the legacy well will help us with three different objectives of MMVs. The first is conformance. So it lets us know if our injection of CO2 is taking place as planned into the subsurface formation. Second, containment. It lets us know or make us feel ensured that the CO2 injected is going to stay below the seal in the injected zone and not going to make its way to the surface through the legacy wells or through faults. Third, contingency. So this legacy wells for MMVs will also help us in terms of identifying any anomalies and have a contingency plan, or even make us or help us stop the leakage if any. So for a successful and safe implementation of a CCS project, the integrity of legacy wells are crucial. So I would like to thank IEW and ExxonMobil for allowing me to share our work in this session. And thank you, everyone. With that, I end my speech.
Mr. Premkumar explained the choice of CCS projects in wells, saline aquifers, and depleted reservoirs. A legacy well integrity assessment workflow, its stages, characterization, risk assessment, and opportunities were explained. Finally, a case study was presented to exemplify their presentation. Thank you so much. I would like to invite Mr. Vineet Bakshi, Director Business Development, LanzaTech, for their presentation on value addition and sequestration of carbon in waste gases, off gases, off refinery and steel ferroalloy plants through novel gas fermentation technology.
Thank you, sir, for the kind introduction. Honorable session chairs, my fellow panelists, and on the industry colleagues and captain out there, a very good morning to all of you. Good afternoon, actually. Indeed, a pleasure to be here and present a view on the subject of much relevance. And certainly, like, thanks to the Technical Advisory Committee and the organizers for giving us this chance to present our views. See, like, if you, I'm sure most of you would have gone through the AR6 report of IPCC committee, which came out in 2023. The report shows that we are already 1.1 degree more than the level of temperature rise which happened in 1850 to 1990. And that too only in last one decade. From 2011 to 2020, there have been like so much of emissions that we have already risen 1.1 degree. And you know, like, why I'm talking about 1.1, because that was something like Ritesh also mentioned. And again, like Santhosh also set the context for me, like what's the importance of CCUS today. So it's, if you look at, this is what IEA the four scenarios, they have presented. And today when everybody is talking about being net zero, the world wants to be net zero by 2050. Like India is also pledged to be by 2070. So why is this important? Because net zero is actually the scenario wherein we are able to limit the temperature rise within 1.5 and effectively bring down the CO2 emission, which this year have actually risen more than 40 gigatons. We want to bring it down, and also at the same time, if you look at the methane, that has also improved significantly. And if you look on the right side, I have shown like if we follow the steps, which is the stated policy scenario, what happens, where our temperature is going to land up, and at the same time, like even the announced pledge scenarios, like a lot of pledge have been made by the nations, and like which was submitted as the INDCs to UNFCCC during the COP 21. And then recently again at COP27 last year when net zero was in focus, we heard a lot of pledge was made. But even if you undertake all those pledges, still we are not going to make it less than 1.5 or 2 degrees Celsius. So net zero is only the way to stand by our target of 1.5 degrees Celsius. And this is something which I like to mention always. The carbon budget which the entire world has to limit itself to 1.5 degree is actually only 500 gigatons. And this is the total emission budget, not country-wise. Out of this, country-wise allocation would be there. So it's not easy, and something more needs to be done just beyond like carbon efficiency. And so how do you reach there? I think these are 5 critical pathways to reach there. Use of renewable energy, energy efficiency, electrification, biofuel, hydrogen, CCUS. And that's why like CCUS is very important. Just a disclaimer, like certain statements in my presentation may look like forward-looking as of now. Your investments cannot be based on that. Just a legal disclaimer which we have to give as past or when you're listed on NASDAQ. So something what I said that if you already just look at the steep rise in temperature, the steep rise in CO2 emission which has taken place in last 15 years. And I said like already 1.1 degree above what happened in last 150 years, that has happened in last 10 years. And when we talk about like reducing carbon or capturing carbon, like carbon, I think we all know, the carbon is actually the foundation of our materials, right? We use carbon, like be it your surfactants, this is eventually that, you make the clothes which we wear, the shoes which we wear, I think everything has like carbon in it. I think even the planes we fly, right? And this is all what we have been doing. I'll show you. It may seem like a fantasy, but this is what we have been doing at LanzaTech. And we at LanzaTech, we thoroughly believe that there is enough carbon above the world. And what happens is, like what matters is where your carbon comes from, which actually defines the climate future. And as I said, the world has enough carbon. A simple process we follow that, we just recycle and transform carbon and put it back to earth. That is like what we have been doing. And so this is what we do. This is our running plant, which has been running for last 5 years in China. Based on steel mill emissions, we have been taking that and making ethanol. And then ethanol has been used for gasoline blending, but also for a lot more things, which I'll be discussing in my subsequent slide. And the best part is that like LanzaTech is a Skokie-based company. Skokie is a place near Chicago. We started out 17 years back, and 2023 Time magazine, they rated us as one of the 100 most influential companies in the world, making extraordinary impact in the world. And so what the process is, this box is actually the heart of the process. We take a feed gas. Any emission you have, it could be from ferroalloy gases, from steel mill gases, or even like in case of refinery, you can have a refinery PSA waste gas. Any gas which has like CO2 and hydrogen in it, we compress that gas, we treat that gas, and then we like feed it to a reactor. So what we are doing differently is actually we are doing it through a gas fermentation process, and that too by the use of naturally existing microorganisms. Like what Ritesh was mentioning, so these are actually naturally existing microorganisms. These are, which actually act like a catalyst in a refinery. Like any process you have in a refinery, you fill your reactor with catalyst, and what we do, just a handful. And believe me, they're just a handful of microbes, which we feed in the reactor, and then they inoculate themselves and multiply. And what that bug does is actually it feeds on like CO, and it takes like CO. You have CO2 and you have hydrogen in the feed stream. It takes that and converts that into ethanol in a single step. So in a single step, you are actually not only capturing the carbon, you are actually transforming it. And then at the downstream, we have a conventional distillation process which is there, which is used in a typical 1G plant also. And the best part is, if you don't have a gas emission, but you have like biomass feedstock, MSW feedstock, we can gasify that. And at the back end, the process remains same. Ritesh also let us upon like e-fuels. You have the CO2 available. You take it along with hydrogen through reverse water gas shift, and then like back to the back end, the process remains the same. So what flexibility the process gives you is actually, it's it could run on multiple feedstocks, and I'll be showing that. And then like once you have ethanol, so ethanol is actually a building block, which you have for the chemical industry. You dehydrate ethanol, you get ethylene, and all of us know, like what all ethylene can do. Via MEG, you make MEG out of ethanol. You can make EVA. You make the soles out of it. From MEG, like you can make like PET resins and PET fiber, the clothes we wear. Or also, then through our sister company, like there was also technology which I'll be touching upon later, which is actually ethanol to SAF conversion. So wherein again we make a sustainable aviation fuel through alcohol to jet fuel. And the best part is the waste microbes, so the microbes, they keep on multiplying, and they are, we keep recycling the microbes, but there is a bleed of microbes which needs to be taken out, because otherwise they multiply very fast. Like even those waste microbes, they are being sold as a very high animal protein feed, I think in a plants in China, which fetches a lot of value. So in a way, like what you are doing, you take the waste, you convert it, and then again you capture it back, or you keep it in your clothes or material. So this is what we actually refer to as the circular economy, total carbon like sequestration. And like we all know the importance of a circular economy. What it helps you actually in, it actually like helps you in minimizing your resources, minimizes the waste, like helps maintain a symbiotic relation within various industries where the waste of one can be used as a feedstock. And that is exactly what we are doing at LanzaTech. And we already have more than 1,500 patents, and close to 600 are pending. So that makes it like 2,000 patents in all. And our mission has always been, to change the world. So far, like through the 4 operating plants which we have been able to abate 300 kilotons of CO2. And there are 2 more facilities which are right now in commissioning phase. Like once they come on stream, so we'll be able to abate 500 tons of CO2, and this is on LC basis. And the annual production of ethanol, once all 6 plants are running, would be close to 300 KTA. And how we say at LanzaTech is actually, we are on a mission of abating like gigatons of carbon, because it's not just 5 or 6 plants. A lot of such plants needs to be there, like if we want to actually abate carbon from the world. So just a bit of chemistry, like what are we doing? When we have the steel mill gases, if you look at a steel mill gas composition from a blast furnace or the basic oxygen furnace, so CO is a major component. And if you look at the carbon efficiency which you get over there is close to like 33%. But at the same time, once you use MSW or biomass feedstock, so the carbon efficiency then rises, depending upon whichever process you are using. And in case of refinery fuel gas, because a refinery fuel gas that has like CO, CO2 and hydrogen, all of it, your carbon efficiency is actually like 100%. Because if you look on the right side, in fourth case, you don't have any CO2 over there, which you are emitting. And similarly, in case of the e-fuels, again, if you look at the carbon efficiency is 100%. And like as you say, the proof of pudding is actually in eating. We are not just saying something. This is actually happening. I think it has been journey of 15 plus years from lab to pilot to demo. And then on the right side, you look at these are the first 4 are the plants which have been up and running. And last two, the first is based on steel mill waste emission gas. The next 3 plants are based on like ferroalloy waste emission gas. The fourth, that IOCL one, which is coming up right now, that takes refinery fuel gas feedstock. And the one plant which is again coming up in Belgium, that's a plant of ArcelorMittal. They have a steel mill in Ghent in Belgium. We are using that. And then, as I said, CO2 abatement, and you make a lot of projects. One thing I would like to reflect, the product quality. If you look at the plants which are running as of now in China, they have a certification by RSB and ISCC Plus. Now, those of you who what is RSB is actually the gold standards of sustainability products. So the point in case I'm trying to make is the products has been, the quality of product is such, that it is used all across Europe also for making further value-added products. I'll just show you. And this products actually fetches the carbon credits to the clients who are manufacturing it. That is how it will help. These are the 4 plants. And if you look at the capacity, they are proper commercial scale. The first one was close to like 40 KTPA, then 65. Last one is 60. And this is the one plant which is coming up at IOCL Panipat, 35 KTPA. And the one I mentioned at ArcelorMittal facility in Europe, that will again be 64 KTPA. Yeah, so again, the plant coming up in IOCL Panipat. So the point I was trying to say, it's not about just making ethanol. We don't stop here. You have ethanol, it's a building block. You make ethylene out of it. There are multiple number of olefins we can make, and those will be the pure like green molecules. You make like polyethylene, MEG, PET, fiber, clothes, and then sustainable aviation fuel. That also you can make. And if you look over here, like these were the first flights. So the lady sitting over there, she's our CEO, Dr. Jennifer Holmgren. And this is the flight which was made by All Nippon Airways in 2019, which was from Seattle to Tokyo. And there was also a flight, which I'll be showing in subsequent slide, which was made by Virgin Atlantic in 2018. And that was the first flight which was made by any fuel.
Mr. Vineet,
you
just have 1 minute to summarize.
So, like this is what I said that we also have a process wherein you can convert ethanol to sustainable aviation fuel, and we all know that mandates of SAF are there around the world. I think India also have been mandated to blend it 1 to 5% by 2027, and the testing of this SAF has been done by NPCC, and there have been 95% reduction in contrails and the soot particles on the quality wise. And this is the best thing actually, what we are doing. We are used, we have been last couple of years, we have been using that ethanol molecule, and Coty, which is the leading fragrance manufacturer, they have made perfume out of that. Zara has come up actually with limited collection out of that clothes. Migros, Mibel, they have come out with the packaged bottles. And all of this actually has been made from the emission out there. L'Oreal came out with a sustainable bottle. Yeah. And over there you can see Sir Richard Branson is there. He's with our CEO. That was the first flight which was taken from Gatwick to London in 2018. The first flight ever made on a sustainable aviation fuel. And then, of course, we'll, with surfactants, like we have our partners, Technip, which helps us in making SAF, and India Glycols, which help us in making surfactants. And this is actually the shirt, if anyone wants to see, this has actually been made from the steel mills waste emission, which were there in China. We got it converted to ethanol, and then they converted to MEG, and then to PET, and then to a shirt. So this has actually been sold in the market. So this is like something, which no one would have thought as of now, right? So, yeah. And, yeah, so this is, and just one thing, like this is not, we are not just stopping at ethanol. Through direct route of microbes only, we are also studying how to modify those microbes to directly in the same plant make acetone, isopropanol, MEG, and more than 100 plus chemicals. And why, this is something, which Ritesh also highlighted. See, there are certain pathways, which are not possible like thermodynamically. So that is why, if you talk about the next revolution thing after like your artificial intelligence is actually your synthetic biology. And that is what we have been doing in our labs, So what I'm saying is, like today you make a plant for ethanol, and tomorrow just only with the change of microbes from the same plant, you can actually make, like next-gen chemical like IPA, acetone, and MEG. And we all know the value which a petrochemical fetches you vis-a-vis fuel. Yeah. So just a time to rethink carbon. Thank you. Thank you.
Thank you, Mr. Vineet. Next, we have Mr. Raj Kiran. Mr. Raj Kiran is a PhD assistant professor at Petroleum Engineering, Indian Institute of Technology. And he'll be walking us through evaluating and enhancing sequestration potential and efficiency in plutonic and volcanic rocks in India. Over to you, Mr. Raj Kiran.
Thank you, Manan. So today I am going to talk about carbon sequestration. So whatever we are dealing till now, like one of my colleagues talked about carbon sequestration, other were related to carbon utilization. But ultimately we have to sequester carbon, and I will tell you why, okay? And there are different avenues for carbon sequestration in India, so we will look into that. So let me start with some open questions, okay? So there are different avenues. One of them is plutonic or volcanic rocks for carbon sequestration. So we want to see whether it is feasible in India or not, and then what are the various sequestration potential of these sites. Is there any interplay of mechanical or chemical properties? If so, then why? And can we enhance that sequestration potential? So these are some open questions which I would like to discuss today, okay? So there is some outline where I'm going to introduce the topic with the importance of CCUS, what is the significance of geological sequestration, what are the different mechanisms, what are the probable sites in India, then what we need to understand, like from different modeling perspective. And then I will show you quickly a few results, and then we will discuss some portion about those results. And finally, I will give you some take-home points, okay? So if you want to look at the carbon sequestration, so basically if you look at the India's goal, we are talking about carbon sequestration always, like we want to mitigate carbon CO2. But whenever we talk about the utilization, ultimately whatever you produce, it is going to come back into the atmosphere. So if you want to actually mitigate that CO2, you have to sequester somehow for a longer term, okay? So also if you look at the history of Earth or any planet, right? So ultimately once it comes out in the atmosphere, if you do not sequester it, it is going to result in the problems like right now you see the Mars atmosphere is full of CO2, right? So we don't want to do that, right? So that's why we need to sequester it, right? Ultimately, that is the bottom line we have to opt for. So for that, there are different avenues, right? So there are one of such avenues is plutonic and volcanic rocks, right? So these rocks are basically like calcium, magnesium, and iron rich, which can sequester CO2 in form of carbonate, right? So for these, we need to understand what are the different properties of these rocks. So basically, it has low permeability, low porosity, it has high strength, it has conducive minerals, for example, pyroxenes. You must have been hearing these minerals. So these minerals are conducive for carbon sequestration. And for these minerals, like we sequester in form of mineral trapping, right? There are other trapping methods in geological sequestration, like capillary trapping or solubility trapping. But we want to, if we want to sequester for longer period, we need to focus on the mineral trapping. So let us see if it is possible in the plutonic or volcanic rocks. Basically, the mineralization process is based on the CO2 dissolved. If you have divalent ions in the like in the host rocks, then it can sequester CO2 in form of the carbonates, right? So if you want to evaluate like how much is the sequestration potential of these rocks, we need to go for the modeling or the experimental studies, right? So we have done few studies. Let me show you few of these things. So once we start with the reservoir modeling, we need to first verify our model. So there are two ways. One, we validate with the grid sensitivity analysis, where we vary the grid like size and we see how much error we are getting. So based on that, we come up with like what should be my grid size in the reservoir model, and then we go for the validation. In this study, we validated one of the model with some experimental data which was done by Wang et al. In 2022, and we found out the error was within 20%, which is good enough number for reservoir simulation data. Okay. Okay, so now if you want to look at what is the sequestration potential, sorry, it moved fast. I don't know. Okay, so if you are looking at the sequestration potential, there are different avenues. Specifically, if you are looking at plutonic or volcanic rocks, these are Raj Mahal traps or Deccan province, right? So if we want to see what is the sequestration potential in these rocks, we need to know what is the mineral composition. So based on the XRD data, you can quantify what are the different type of minerals. So if we know what is the volume fraction, in the reservoir model, we can introduce what is the chemical composition of these rocks are, right? And then we can see that what is the temperature and pressure conditions in which these rocks are present, right? So based on that data, you can find out that how much CO2 moles or like gigaton you can sequester in these host sites, okay? So the bottom line, based on these modeling effort, we found out that if we start now, we will be able to see the mineralization result only after 20 years. So the time we want, this is the time to make that decision. If we want to do it, the sequestration or not. If we don't want to do it, we might regret, or if we want to see these results, we have to wait it for 20 years. That might be too late. I'm not trying to give you a doomy picture, but that is the reality. Okay. So anyways, so basically if you have these type of minerals like pyroxenes or plagioclase, like these can be converted into the carbonate rocks. One of the very conducive mineral is based on the magnesium silicate, which can be easily converted into the magnesium magnesite, which is magnesium carbonate. And that is the basically, if we'll, based on our simulation studies, we found out that the magnesium has lower rate of lower timeline for the conversion. Okay. with this, I will also like to show you there are different ways people are trying to find out that how we can sequester or can we enhance this sequestration potential in these rocks, right? Because these rocks have low porosity and low permeability, right? So how can we enhance it? Either you can implement the fracture geometry, right? Like you can fracture, most of you, if you are like following the oil and gas upstream industry, you must be hearing about hydraulic fracturing, right? So we can fracture the rock and we can enhance the sequestration potential. That is our intuition. But is it really? So we tried to simulate that, like the fracture geometry with the normal geometry, and we see that like once we fracture the rock, right, so it has achieved some steady state. If you can look at like, so anyways, so if you look at these two pictures, one is saying that without fracture, other is with fracture. So clearly the mineralization potential of the with fracture part is more. However, you can see that it is achieving the steady state after 20 years. That means whatever Mg magnesium silicate was there, it has been consumed by the CO2, or it has trapped the CO2. Basically, if it is without fracture, the timeline will be larger, right? Like it will take much more time to form the carbonate rocks, okay? So these are the two things which we want to discuss. Based on our study, we found out that like if we inject at around almost 1781 barrel per day of CO2 in Rajmahal traps and Deccan province, we can sequester almost 6.69 gigaton or 380 gigaton in the Deccan province, which is much more like the quantum will be quite high if you want to sequester on these rocks. Okay. However, there are other avenues. My colleague will be discussing about the potential in other avenues along with this in the other session. If you want to attend, you are most welcome. Anyway, so basic like workflow, if we want to do some experimental work, we have to do XRD, FESEM, or we have to look at like how the Raman spectroscopy data is to characterize what is the exact mineral. Or so for that, we have done one sample work from one of the rocks present in the Dhanbad region only, which has the similar mineral characteristics like Rajmahal traps or the Deccan province. And we found out like there is one mineral which is diopside, right? So there is a diopside where you can see that like the diopside can be converted into the magnesium, can be the host rock for carbon sequestration. Okay, so for the XRD data, actually we tried to like corroborate our presence of diopside in that particular material with the Raman spectroscopy data, which completely matches, and therefore we concluded that we put the hypothesis that the diopside can be used for carbon sequestration. Okay. To look at the carbon sequestration potential, so you need to do a long-term experiment. However, like in the shorter time, we can see that if there is some indication of carbon sequestration or not. So for that, we put the same rock in the CO2 environment and the pre-CO2 environment, and we figured out, like we saw there are some initiation of like carbonate rock formation, which we cannot say because that is based on the modeling data. So we are trying to do a long-term experiment, but the data is not yet available. But we can see there is a molecular breakage of the molecular structure or fatigue stratification, which is maybe like the initiation point of the carbonate rock formation. Okay. And for that, like if you want to see the long-term potential of these rocks, we looked at based on the simulation, and we found out that like diopside can be easily converted into the carbonate rocks. Okay. One of the main challenges in these rocks is the injectivity issue. Okay, because these rocks has very low porosity and permeability. So even if we want to inject it, how can we inject it? So you have to fracture it, right? So we need to understand the fracturing characteristic. For that, we did some geomechanical studies, and we found out it can be like if we inject around 2000 psi or something, like around 2000 psi pressure, it can be fractured. These rocks can be fractured, or the hydraulic fracturing is possible in these rocks. Okay, so these are some glimpses of the research what we are doing, right? With this, like, we are also looking at the fracturing and its interplay with the mineralization. We are looking at what is the mineral assemblage, which is the main point for any host rock if we want to sequester it. If we want to fracture, like even if we fracture, there are risk of plume migration, right? So we want to see that, these are all ongoing works. We are also trying to carry out like some long-term experimental results where we can show you that what is the exact sequestration potential for these rocks. Anyways, so these are some points, definitely your Deccan province and Rajmahal traps has CO2 sequestration potential. If we are looking at the actual mineral trapping form, which is the basic way how the nature sequesters CO2 for long term. Okay, for that we need to look at the mineral characterization, like how we can get into the insight of like what is the exact mechanism for sequestration. Fracturing can be effective, but it has some repercussions, like it might have plume migration, or these things might be might happen. So we need to look into that aspect deeply. Injectivity issues can be addressed using the hydraulic fracturing, but we need to do much more thorough study. Okay, so these are the works we are doing. Like basically, we are focusing on energy transition based on basically two fronts. One is related to the project Shrine, which is looking into the super hot rock potential of India, which has, like we have seen, like we are looking into that different aspects. Also, we are looking into the underground hydrogen storage as well as carbon sequestration in our lab, as well as the modeling environment. So these are some of the projects which we are working on. If you are interested, please feel free to contact us. We would like to collaborate. With this, I would like to end my talk. Thank you. If you have any questions, we can discuss at the end of the session. Thank you very much.
Thank you, Mr. Raj, for staying on time. Mr. Raj explained the carbon sequestration routes based on the geological routes. The simulation, modeling, and experimental techniques were presented, and the time criticality of this decision was emphasized. With this, I would like to invite Ms. Jyoti Verma of ONGC Energy Centre. She is a junior project associate, and she would be presenting the initiatives of ONGC Energy Centre for carbon dioxide valorization.
Good afternoon, ladies and gentlemen. Thank you, organizers, for giving me this opportunity to present the initiatives of ONGC Energy Centre that we are working in the area of carbon dioxide valorization. So ONGC Energy Centre is an R&D unit of ONGC, which is working in alternate energy areas. It has been set up in 2005. The modus operandi is in collaboration with various national and international institutions, including the CSIR institutions. So we are working on the proof of concept projects, scaling it up to various TRL levels depending on the outcome of the projects. These are the areas that we have been working, and we are open to collaborate. It's geothermal energy, hydrogen, biotechnology for energy, carbon dioxide sequestration, then uranium, helium, wastewater treatment, and solar thermal as well. We have a vision to meet national energy needs of tomorrow in a clean and sustainable manner. So as the previous speakers have already commented and why we need to tackle the CO2 issues, since India has been mandated by the Paris Agreement to lower its CO2 emissions, and we aim to go net zero by 2070. So therefore, it's our responsibility to work in these kinds of areas and support the technologies. So I would like to give various insights on the catalytic valorization of carbon dioxide. We know that the carbon dioxide that has been captured from various industries is mainly a waste at the moment. Very small percentage of it is being used to convert it into various value added products, which at present it is urea, then methanol and other carbonates. So I would briefly covering the thermochemical processes, the photocatalytic processes, and the biochemical processes that we are supporting. So the first one is photocatalysis. So we are working in collaboration with IIT Madras. There we have a fabricated photocatalytic reactor system in which we are using a photocatalyst tin oxide, and it has been modified using graphene oxide to improve its efficiency. The plasma process is having the efficiency of about 25 to 30%, and it has scalability challenges. So only the proof of concept model was supported under this kind of project. The various factors that affect this kind of process are difference in the catalyst, then the distance between the electrodes, what kind of electrodes are being used, what kind of catalyst is being used. The emphasis is more on the indigenization of the catalyst. What is the electrolyte being used? So these are the factors that affect the efficiency of the process. So this is the publication that we have. Those of you who would like to go in more details can see this paper. Next, we have the project with Maulana Azad National Institute of Technology, Bhopal. There we have taken two projects based on plasma photocatalysis. So plasma process is there with the nature during thunder and lightning. It is a kind of chemical reaction where charge carriers are generated and they continue to generate current. So biocatalyst has been developed under this process, which has been isolated from rice husk. So a patent has also been filed for this particular project. There you can see the catalytic reactor that has been developed by the institute, and the major issues in this kind of process is the coking, that the catalyst gets coked and therefore the efficiency gets lowered. So these are the various types of plasma reactors that are available, and this particular project was based on the dielectric barrier discharge plasma. So the challenges regarding this process is the temperature of the system goes up after the reaction starts. So we need to control the temperature by integrating a cooling system with it. So which is called afterglow quenching. So in fact, it has been observed that the nitrogen content in the feed can also limit the reaction rate. So therefore, it needs to be controlled as well. Then this is the application of the plasma catalysis process. It has been reported in various journals that it is used for wastewater treatment, material treatment, then VOC removal, and others. These are the publications. So for some of those of you who like to go in more detail can have an access to this. The next process I would like to discuss is with the Institute of Chemical Technology. There we have developed a chemical catalyst. It is a cerium aluminum oxide based catalyst which can convert carbon dioxide into carbon monoxide, methane, methanol, and it has applications in various chemical industries. I would like to also share that we have developed a hydrogen facility right at this particular campus. For those of you who would like to see the facility, are welcome to visit there. And this particular process is proposed to be integrated with the hydrogen generation capacity via thermochemical cycle. The efficiency of this process has been demonstrated up to 4,000 hours, which is the maximum reported so far as per the global literature. The catalyst has been formulated by hydrothermal co-precipitation technique. You can see the picture of the reactor as well. Patent has also been granted in India, and other patents have been filed in various other countries. So the next is the bioprocess that we are supporting. A lab scale study has been done to convert carbon dioxide in coal bed methane well reservoirs into methane, so that the methane production goes up. So there is an issue of high CO2 content in the CBM wells that we see at ONGC, so in particularly in Bokaro area. So this particular process has been implemented in the well recently, where we are trying to convert the carbon dioxide into methane to increase the calorific value of the CBM gas. The advantages of this process is it does not require any rig intervention, and it is easy to implement, and a certain incubation time is required so that the nutrients and the microbes get cooked, and they can enhance the gas production. So we are the well is still under monitoring. So why we are interested in these kind of processes is because the carbon management strategy is being developed all over the world, where different kinds of processes are taken up by various companies, and therefore a certain global standard is required to be developed, so that we can jointly take up this initiative to tackle the CO2 emissions. So for more details, you can contact us, and thank you.
Thank you, Ms. Jyoti. Next, we have Mr. Arun Kuniyil. Mr. Arun Kuniyil is a manager R&D at Hindustan Petroleum Corporation Limited, and he's going to talk about HCNG, which is hydrogen enriched CNG. Over to you.
So, good afternoon, everyone. So today I would like to take everyone of you through the journey of a new technology, HCNG technology, and it's a differentiated technology towards decarbonization. Through outline, I will not take you. I know I'm standing in between you and your lunch. So coming to HCNG, the risk of climate control has been there for some ages. It's not a new topic. And if you try to connect the dots, we have been moving our fuel mix from diesel to petrol and from petrol to CNG. Inherently, what we have been doing is you are decreasing the carbon content in the fuel. That will ensure that carbon emissions are less. So now, where do we go from CNG? CNG is already predominantly having methane. That is a single carbon molecule. So the only answer left is to add hydrogen into it, or else ensure that hydrogen is there in CNG so that CO2 emissions are less. So HCNG is defined as any mixture of fuel which can have up from 15 to 20% of hydrogen, and rest is CNG. And in one of the recent reports by Niti Aayog in Action Plan for Cleaner Fuels, they have identified HCNG as one of the potential alternative for CNG. What are the major benefits of having HCNG instead of CNG? So we can see that few of the listed items are, we can use this HCNG in CNG designed materials. It can be storage, it can be transportation, it can be CNG engines. These are all compatible. And advantages, we have lower CO2 emissions, higher mileage, since hydrogen is there, it is having more calorific value, lower CO emissions because at high temperature, carbon monoxide will get converted to CO2. Because of all these, HCNG will be acting as an interim solution in between the current hydrocarbon-based fuels and the future hydrogen fuel. Coming to the production methods of HCNG, the most simplest method that anyone could think about is you just add hydrogen into CNG. That's as simple as that. The only challenge here is from where do we get our hydrogen? Conventional hydrogen is produced in the method called steam methane reforming, which emits huge amount of CO2 as well as it requires water. The other option which companies have tried is you do a partial steam methane reforming. So you ensure that the hydrogen content in the CNG is only up to 15 to 28%. But even in this process, you will emit some amount of carbon dioxide. The third option is natural gas pyrolysis. So here the concept is from methane, you try to split or extract the carbon content from the methane. So if you compare with steam methane reforming and natural gas pyrolysis, the energy requirement, if you see the total reaction of methane and water giving CO2 and hydrogen, it is around 165 kilojoule per mole. And in natural gas pyrolysis, it is almost half of that. So if it was less energy intensive, why didn't people move about it? So the challenge comes here is the carbon. Normal natural gas pyrolysis, if you do, you will end up with amorphous carbon, which is of low value. So here HPCL has developed this unique patented technology in which you do natural gas pyrolysis and you end up producing carbon in such a form that it is one of the most highly valued form of carbon, that is carbon nanotubes. So in the briefly, if I explain the process, natural gas is fed into a reactor system which we call as HPCNG technology, and on one side you get a direct product of HCNG which contains 15 to 20% of hydrogen and rest methane, and the remaining carbon will be in the form of carbon nanotubes. I'll just briefly explain some salient features. I can have natural gas or biogas or refinery fuel gas as my feedstock for this particular technology. When you produce HCNG from natural gas, it can be considered as carbon neutral because you are not emitting any CO2 emissions into the environment. But if you are using, say, biogas, this becomes a carbon negative proposal. And the products are HCNG and multi-walled carbon nanotubes. The core part of this technology is the catalyst, where the carbon is forming into nanotubes. And that catalyst is a modified refinery spent catalyst. And a unique patented technology is there how you activate this catalyst. And reaction temperature is much lower than what is required for natural gas pyrolysis, which comes in the order of 1000 to 1200 degrees Celsius. And the most unique part of this technology is nil carbon dioxide emission and nil water requirement. Coming to the novelty of this technology, on one side we have novel reactors and internals. So this is a reactor which is working in the form of a bubbling fluidized bed reactor. Since carbon is forming as solid carbon, even though in form of nanotubes, you have to handle solid material. So you should have distributors which are designed for meeting the requirement as well as to stop any choking inside the reactor. And the reactors are designed in a lead lag mode of operation so that it is a partial batch operation. So once you create enough CNT, you move from one reactor to the next reactor. Coming to the catalyst, it is an in-house developed catalyst As I told earlier, it is formed from one of the refineries' spent catalyst as a support material, and it can create highly valuable carbon nanotubes. In the unit operation, there are some unique features. So the catalyst, initially it's a bubbling fluidized regime catalyst, around 50 to 100 microns. And when carbon gets deposited on this catalyst, the size of the catalyst changes, density of the catalyst changes. So how do you deal with those changes? So that is the part of unique features which is coming in the unit operation. And broadly, if you see the challenges and opportunities, a rapid catalyst deactivation is what people have been observed for methane decomposition reaction. So here we have a moderate activity catalyst which will not choke, which will not cause any blockage to further methane getting converted. Another is low reaction time on stream. So here with lead lag reactor configuration and a novel distributor and reactor design, we are overcoming that challenge. Now coming to CNT quality. People have been trying to prepare CNT using decomposition reaction with ethylene, with methane. So the reaction temperature plays a critical role. Normally CNTs are formed above 800 or 850 degrees Celsius. Before that, if you try to do decomposition, carbon will be in form of amorphous carbon. So this is a unique catalyst which maybe later on I'll show you that graphs wherein something called tip growth mechanism is facilitated, which will ensure that even at lower temperature, you will get a carbon nanotube as the product. And process viability we can achieve because of low catalyst and low energy requirement. Coming to technology demonstration, we have carried out demonstration at a pilot plant facility in our center. Around 50 kg per day scale we have operated, and operating temperatures was less than 600 degrees Celsius. This is the photograph of the facility that we are having, and already 4 patents are granted and much more are filed on this particular technology. Coming to the sustainability concept, as I told, on one side we have a refinery spent waste material which we are converting into a catalyst, and the feedstock can be from bio origins, which will ensure that we have a negative carbon technology. In the carbon nanotube, as sir was telling, we convert carbon into any form of fuels. It will inherently go back to the atmosphere in the form of carbon dioxide. So but you try to capture carbon into such a material that it is having very high strength, and wherever you are using, it will stay as solid carbon. So you ensure that this is a mode of sequestration which will ensure that carbon doesn't go back to the atmosphere. Just a quick comparison of all the technologies. Here we can see SMR. Water electrolysis is there, where we can produce hydrogen and then blend into CNG to form this, and methane pyrolysis, and the last one is HCNG technology. So I just want you to show 2 items only here. One is process CO2 footprint. So here we can see for SMR, it will require around 6 kg of CO2 per kg of hydrogen, that is on thermodynamics. In practical, it will be around 13 kg of CO2 per kg of hydrogen. Whereas in this process, there is nil CO2 emission. Water footprint, in SMR, we will need around 4.5 kg of water per kg of hydrogen. And if it is water electrolysis, it will be 9 kg of water per kg of hydrogen. But in this case, you are not having any CO2 emission, and we are not consuming any water, ensuring that this is a sustainable technology. Here, for people who are interested in a little bit more of technology, on the left side top, we can see the catalyst. It is a spherical catalyst, on top of which we have unique elements which are deposited or impregnated, which will ensure the catalyst activity is maintained. And on the second figure, you can see the carbon nanotube. Typically around 50 to 100 is 100 nanometers the diameter, and length is coming around 10 to 20 micrometers. And the tip growth mechanism you can see, so that it's a unique catalysis form of action wherein carbon gets deposited on top of the active site of catalyst, then it moves through the catalyst and reaches the base, and at there it extrapolates. So the active site of the catalyst, it traverses and ensures that for every fresh molecule of methane, it is available for further cracking. CNT applications, many of you might know it is a most exotic material. It is having very high tensile strength and unique properties in thermodynamics as well as heat transfer. So we are studying or preparing applications based on bulletproof jackets, tribology, that is nano lubricants. We are also working on using this CNT for anti-corrosion materials. But coming to the carbon market, so here I wanted to take through the annual market size as well as carbon price. All are carbon-based material. Graphene, if you see, it is one of the most costliest form of carbon, but the market size is less. And if you see coal, the market size is the highest, but value proposition is low. So somewhere around middle, you can see carbon fiber and carbon nanotubes. So those currently have decent enough market and decent enough price. So we target that market. That is where the cash will flow in. Coming to the conclusion of my presentation, any technology can sustain only if it can click on the right check boxes. And broadly, it can sustain if it is on economical side it is beneficial, and environment side also it has to be beneficial. So if you see here on the economics, our technology is having low cost catalyst because we are repurposing one of the catalysts and impregnating our required materials. The carbon nanotubes formed, which can be of high value, will ensure that a premium product of hydrogen enriched CNG also can be sold at CNG price, because customers are not going to come up for a premium for a low carbon fuel. So we have to entice them with same price. And the last one is integration with CBG plant, which will result in a carbon negative hydrogen production. Coming to environment side, there is no CO2 emissions from the process, and the outcome of the process is also carbon nanotubes, which will ensure that in recent future those carbon are not going to go up as carbon dioxide. And there is no process water footprint is required, no water is required. And because of all this is one of the most sustainable technologies for decarbonizing our minimum carbon fuel, what is HCNG. Thank you. So this session of in our energy transition, we began with a HPCL researcher, and we are closing with another HPCL researcher, and still we are I think just on time. Anybody, if you are interested in understanding this technology or knowing about more, or else for collaboration also, we have a stall in hall number 2. Now stall number is 10. I have a working 3D model of this particular technology. If anybody is interested, you are always welcome to visit. With that, I'll leave the stage. Thank you.
Thank you, Mr. Arun, for an excellent overview of HCNG technology. The very striking feature was development of HCNG utilizing the existing infrastructure. So very remarkable pilot scale demonstration and offer of having a collaboration also, visiting HPCL stall. With this, we end of a very excellent round of eclectic presentations.